Hello everyone, myself Dr. Sharmila Pandey, Faculty in Chemistry, School of Sciences, Sage University, Bhopal. Today we will discuss about the transition metals. So in the periodic table, if we see, so the first two columns, they are known as the S block elements. So these two columns. And the rightmost six columns, that is from boron, carbon, nitrogen, oxygen, fluorine, and here helium column, they are known as P block elements. In between, there are some elements, this portion, they are known as transition metals. They have partially filled d orbitals and they may have unpaired electrons. So they show spectral and magnetic properties and they can act as homogeneous and heterogeneous catalysts. So here we can see in the fourth row, so scandium to zinc, yttrium to cadmium, and they from here this lanthanum and lanthanoids and actinoids and other elements are the transition elements. So what are the transition elements? Transition elements, which are also known as transition metals, are elements that have partially filled d orbitals. IUPAC defines transition metals as an element having a d subshell that is partially filled with electrons, or an element that has the ability to form stable cations with an incompletely filled d orbital. So due to these partially filled d orbitals, transition metals possess unique properties. So the characteristics of transition metals we can see are mercury is liquid at room temperature, and apart from that, all other elements are solid metals exhibiting all the characteristics of a metal. They show variable oxidation states unlike S and P block elements. They and some of their compounds show catalytic properties. Their compounds are colored. They have great tendency to form complex compounds and they form alloys and interstitial compounds. If we see the general trends, we can see that any element which corresponds to the D block of the modern periodic table, that is from group 3 to 12, are considered to be a transition element. Even the F block elements comprising the lanthanides and the actinides can be considered as transition elements, but as we can see, they have incompletely filled d orbitals, so they are often referred to as inner transition elements or inner transition metals. One more important thing to note is that zinc, cadmium, mercury, they are not considered as transition elements because their electronic configuration we can see they have filled d orbitals, that is n-1 d10 and ns2. So these elements have completely filled d orbitals in their ground states and even in some of their oxidation states. Like if we see +2 oxidation states of mercury, we can see that they correspond to the n-1 d10. So here we can see the list of the first row of transition elements with their corresponding electronic configuration: scandium, titanium, vanadium. In case of chromium, this is 4s2 3d4, but because of the half stability provided by the half filled or completely filled electron orbitals, we can write chromium electronic configuration as 3d5 4s1, and similarly for copper it can be 3d10 4s1. In case of zinc it is 3d10 4s2, and as already told, for zinc 2 plus also it will be 3d10. So zinc is generally not considered as a transition element. So if we discuss the general properties of transition elements, we can see that zinc, cadmium, mercury are not considered transition elements since their electronic configurations are different from other transition metals. However, the rest of the D block elements are somewhat similar in properties, and the similarity can be observed along each specific row of the periodic table. Several transition metals have catalytic properties that are very useful in the industrial production of some chemicals. For example, iron is used as a catalyst in the Haber process of preparing ammonia. Also, vanadium pentoxide is used as a catalyst in the industrial production of sulfuric acid. These elements form colored compounds and ions. The color is explained by the electronic transitions. There is a relatively low gap in energy between the possible oxidation states of these elements. Transition elements therefore exhibit many oxidation states. Many paramagnetic compounds are formed by these elements because of the unpaired electrons in the d orbital. A large variety of ligands can bind themselves to these elements, and due to these, a wide variety of stable complexes are formed by transition elements. These elements have a large ratio of charge to the radius. Transition metals tend to be hard and they have relatively high densities when compared to other elements. Boiling points and the melting points of these elements are high due to the participation of the delocalized d electrons in metallic bonding. And also this metallic bonding of the delocalized d electrons causes the transition elements to be good conductors of electricity. So these are the general trends we can see in all transition elements, particularly along a row. Now, what is variable valency? We can see the compounds FeCl2 ferrous chloride as well as FeCl3, that is ferric chloride. And here looking at this, we can see that the oxidation state of iron in these two compounds are different. In FeCl2, oxidation state of iron is +2, whereas in FeCl3, oxidation state of iron is +3. So, certain elements combine with other atoms, donating, accepting, or sharing electrons in different proportions depending on the nature of the reaction. For example, iron combines with oxygen to form ferrous oxide as well as ferric oxide. In the formation of ferrous oxide, iron exhibits a valency of +2, whereas in ferric oxide, it has a valency of +3. So, this is termed as variable valency, and this is very common in the transition metals. Other elements with variable valency, if you want to see. So transition elements, nickel, copper, tin, iron exhibits variable valency. Non-metals such as nitrogen, oxygen also show variable valency sometimes. The products formed as a result of reaction with different valency atoms differ in their properties. For example, in the above example, ferrous oxide is non-magnetic, whereas ferric oxide has magnetic character. Similarly, oxygen shows a valency of -1 in hydrogen peroxide, that is H2O2, and a valency of -2 in case of water, that is H2O. So properties of H2O2 and H2O are way different. So these are the facts. So here we have seen overall the properties, general trends of transition metals. What are transition metals? Lanthanides and actinides, because of their field F orbitals, they are known as inner transition metals or inner transition elements. Then what are the general trends, general properties of transition metals, as well as a very special property of transition metals, that is variable valency, I have discussed. So thank you.